Okay, we still have something remaining. Actually, these slides are some review of template and function object, and then we can use template and function object to do more pure algorithms, pure generic programming. We have some example here, and we can also use iterator. This is also another design pattern in this example. If time permits, we'll also introduce something related to STL. 但是我想问一下，就是大家有没有同学大作业已经做完的？因为我们下次还有最后一次课啊，就是如果有同学提前做完了，因为我们延期了嘛，但是呢，如果有同学提前做完了，那么下次课呢，我们可以找1组到2组的同学呢，展示一下。就是1、2位同学啊，不是1、2组，因为都是个人作业，展示一下自己的这个大作业。那这样的话呢，我们可以给个，比如说那个2分的加分啊。当然这个要展示的效果比较好哈，我们会根据展示的效果来评定哈，也让大家能够看看其他同学的这个完成情况。但如果是都没完成的话，我们就安排，比如说讲一点点 STL 啊，那这部分呢，并不是我们一定要讲的内容，因为大家其实通过自学呢，这个用法什么的应该也都还好啊。有同学做完了吗？我们的大作业。Okay, you may think about it, and we will put on. Oh, that's great. That's great. 很好啊，我看到有同学回答有做完的啊。那做完的同学呢，可以 volunteer， 我们做一个课堂展示。这样的话呢，也促进一个课堂交流吧。其他同学也可以学习一下，看看其他同学就完成的这个作业情况是怎么样的啊。那这样的话呢，我们可能就会压缩这个 STL， 我们甚至可能都不讲 STL 了。这样的话，我们把这个时间留出来给大家呢做这个大作业的展示和交流啊。根据展示的效果呢，我们会给个最多比如说2分的这样的加分啊。我们会在网络学堂提供这个报名的这个链接，大家注意啊。Okay, so this is a review of actually in this class we 我们看看同学的报名情况哈，我们在网络学堂提交一下这个链接啊，看看大家的报名情况。如果是比如说没有同学报名，那我们就肯定要讲啊。如果有同学报名呢，我们就那个Okay, let's continue our class. So in this semester, we have learned this OOP programming. Actually, we are not only learning OOP, right? We all know that CPP language is very important, right? So you know even Jeff Dean. I'm not sure if you know this Jeff Dean. This is I think this should be spelled like this, right? This is Google AI head, right? This head of Google AI department, and he mentioned that he wants to use CPP language to implement those AI models. However, they did not do that. They failed. But that means we all know there's the importance of the CPP language, right? And why Jeff Dean wants to use CPP language to implement AI models? Because Jeff Dean thinks the Python, Python language is kind of is maintainable only until the developer leaves the company. That means if the developer of the Python code leaves the company, no one can maintain the code because the readability of the code, Python code, is really not good. This is Jeff Dean's opinion. So it's only an example that I think CPP language is still very important. So because we are learning this OOP programming in CPP language, we have to learn something related to generic programming, right? So in this OOP, in this thread, we have learned class, objects, inheritance, and polymorphism, and then this OOP programming, and also design patterns, right? And in this thread, we have learned a template, function object, and lambda, right? Lambda extraction, and also generic programming, right? So first we review this function object. So because lambda expression actually is function object, so we still use this function object for better understanding. In this example, we want to compare the student's pass rate, to compute student pass rate. Okay, so this is score of the student, and then this is the class for checking whether the score passes. So this is function object because we have already this operator function call. So we'll check whether the scores passes the baseline, right? And this baseline is passed in by the constructor, right? By constructor. So this is function object. So this is how we use function object. Originally, we pass in the baseline, and then we compare with the baseline to check whether the score passes or not. So this is how we use function object. And then this passing rate is to compute whether the number of passes, right? And then divided by a total number of the scores. So now we are passing in a function object as a parameter, right? And this function object is called here. So because function objects are typically passed by a value, right? So one suggestion for our students is to not write very large function objects. So there should be we should try to reduce the members as much as possible so that the class is not very large. Then this is passing rate. Right? We use function object to check whether it's passed or not. Then we can compute. So for different array of scores, we can compute whether pass or not. Right? So For this function object, by default is 60, right? 60 is pass. However, we can provide other parameters here. For example, we provide 75, then only this one passes. So the passing rate are different. Right? So by default, this one is 60. Right? So 3 passes. So this is different. We can also use member function to modify the baseline. Right? This is an easier way to change the function object. Right? Okay, then that is function object. Now we want to use template, right? Because sometimes scores are different. We may have 0 to 100, right? We may also have ABCD, right? There are different types of scores. Then how to sort them in the different type of scores using the same passing rate? How to compute same passing rate for different scores? So this is why we use template. Okay, then this is how we write template. And also, we need to pass the type T here, right? Because, you know, this function object also needs to compare different types of scores, right? So that's why we also pass this type T here, right? So we can use the function object in this way. However, we need to define this isPass here, right? We need to redefine the isPass because here we know that now isPass should be a template, right? Template. So we define the template like this. This is isPass. We have the type. Then we can have a baseline here, and then we compare the baseline. We pass in the baseline by constructor, and then we can compare it. Right? If we want to check whether a score object passes or not, scores needs to be comparable, right? Because we need to compare. For example, if we use score here, then we need to compare scores, right? That's why we have overloaded this operator, right? So that scores can be comparable to each other. Then in this way, we can provide a baseline score to the function object, and then we can compare different scores. Okay, so this is the template function object, right? So this is how we use the template function object. Actually, this may not be a very correct word. Function object from a template class, right? This is a correct name. Then we can use passing rate in this way. So we provide isPass here. And then for this function object, we provide a score as a for the constructor, right? This is the object passed into the constructor of the function object to construct the function object. Okay. So this is the way we use template in function object. So it's kind of you know, complicated, right? So anyway, this function object is called predicate. So we have a name for this, predicate. Because this predicate is typically used to compare, right? To compare and return true or false. So predicate actually is a function object, function pointer, or lambda expression that returns true or false, right? True or false. So it is typically used as an argument in the algorithm and typically for comparison, we know, right? Or either comparison or check, right? Typically checks whether the element satisfy a given condition. So this is predicate. If it satisfies the condition, then return true. Otherwise, return false. So this is predicate. For another example, to show the predicate, we use COUNTIF. We want to implement the COUNTIF. So COUNTIF is to count the elements in the array, the number of elements in the array that satisfy the predicate. So this is the predicate. So this predicate, the type of predicate is passed in by template. So this also, the elements is also template parameter, the element type. Then we can count. So this is COUNTIF using template and predicate. So predicate is also, is also used as a template parameter, like this, right? Okay. And then we can define the passing rate in this way, right? In this way. So we have this passing rate. We also have this class T and the predicate, and then we can call COUNTIF for array and num and isPass, right? isPass. So this passing rate is defined corresponding to this COUNTIF, corresponding to COUNTIF. So you have exactly the same data types. And for better efficiency, we use a pointer to enumerate the array of elements. So originally we use this array from the address, this initial address, and then we plus I to get element. However, a pointer actually has better efficiency, So we can do this. We have the pointer, start and end. Then we can plus the pointer, right? So the compiler will depend on the type of the data, depend on the type of the element. The compiler will plus the address. For example, for int, if we plus 1 for the start, it will plus by 4 bytes, right? Int is 4 bytes. So if it is the float or double, then it should be 8 bytes. So the pointer, the plus one for pointer is also overloaded for different data types. Okay. And then passing rate is like this. So we can use pointer to compute the number of elements in the array, and then we can COUNTIF, right? We will compute passing rate. Okay, then let's stop here. The remaining part will be we will learn remaining part next class. Now we start our in-class talk. 第一位同学曹天佑。Okay, let's start our class today. So in our next class, we have learned to this review template. So we mentioned that for better efficiency, we can use pointer to enumerate the elements in the array. So we can use pointer here. So this is a pointer. And then we can, for each time, we can plus the pointer, right? So this is actually this plus of pointer is already overloaded for this pointer. And depending on the different type of the pointer, the plus one will plus a different size of the bytes, so that each time we can access one element in the array. Okay, so this is how we use the template to compute the passing rate. So in this example, so actually passing rate can only be used for arrays. So it couples with the data structure actually. And for a different data structure, for example, for a linked list, actually it's another structure. Maybe some of you may not have learned it, and you will learn it in next semester when we learn the data structure. So for a different data structure, we need to define passing rate function again. So how to decouple between algorithm and data structure? So we need a way to enumerate all the elements in the collection without having to know the storage structure. So this is actually iterator design pattern. So we can enumerate elements in the collection without knowing the actual data structure. So for the iterator, this is the class diagram. This is the aggregate of a set of, actually is a collection of elements. And there's a iterator. So typically iterator has this style, has next and next, this interfaces. And this is actually Java style. So for this Java style, for each time we can check whether there's next element in the collection, and then we can use next to access the element. We all know that in CVP language, iterator works differently, right? We all know that we have this plus plus or ITR plus plus or plus plus ITR. And sorry, ITR. And we also have this to get the element, right? Access element. So there, anyways, for this iterator, there will be some interfaces for us to enumerate elements and also to access the value of the elements. And then we can define our own concrete iterator for a concrete aggregate. So this is the design pattern. So in the design pattern, iterator defines an abstract interfaces for accessing and enumerating elements. And concrete iterator implements these interfaces. In more detail, you should manage current position of the iteration. If you want to enumerate the elements, we have to record where we are when we are enumerating all the elements. An aggregate defines an abstract interface for creating the iterator. And then concrete aggregate has a collection of objects and then also implements the interfaces for this creating and returning the iterator. So this is the iterator pattern. Here's an example. Assume we want to have an exam and we have a class question. So for this question class, it defines a question to be answered. And then it gives a score after the question is answered. And then it shows the correct answer. So this is class question. There are some pure virtual memory functions. These are the pure virtual memory functions. And then there is a class exam. So in this class exam, there is a collection of questions. All the questions needs to be answered in this exam. And then the total score will be computed and shown. So to answer this exam, we need to answer each question in the collection. Currently, it's stored in an array, right? This is star. So we need an iterator to enumerate all the questions in the collection, right? So how to write the iterator? So this is the aggregate. For the iterator design pattern, this corresponds to the aggregate, and this corresponds to the iterator. So we have these interfaces, next and has next. Then we can implement this collection. So we need to determine storage of the questions and determine the enumeration method. This depends on the data structure, actually. So in our example, we have two implementations, one using array, another one using linked list. We will explain what linked list is. Okay, first we can see this array collection. So we are using an array of to store the questions. Actually, there's two-dimensional array. So we can set the question for each element in the array. Then we can create the iterator. This is the key. So we create an iterator. We just pass a pointer to this array collection to the array iterator. Okay, just pass a pointer, current pointer, to the array iterator to construct the array iterator. So this is the array iterator. You can see that for has next, it returns. Actually, you can use a bool. It's better. So this is concept implementation. Actually, you can further polish this implementation later. So we can just store a pointer in the enumeration, and then we check whether the pointer goes to the end of the array, right? Okay. And then for the next, for this one, if we want to access the element, then we can check. If we have a next, then we return the question like this. Otherwise, we can return a null pointer. Okay. Then for linked list collection, actually for linked list, a class item is a key. So actually one item defines one object. One object. This is one item. We can see this. We can see that we have a pointer to the next item. So here is a pointer. This is a pointer, right? So this is a pointer, and this is data. So for linked list, this is a typical structure. So this is an item. Then this pointer points to next item. And then the pointer points again to next item. Okay, so this is a linked list. So it's like a list linked by the pointers. So these are the pointers linked this item together. This is a linked list. Okay, So this is data. Actually, this is question is data, right? The question is stored here. Okay, so this is linked list. And then there are some interfaces. We can get the next pointer, and we can set the next pointer. We can set get question like that. This is item. This is for the basic structure for linked list. Then based on item, we can implement this linked list collection. So for the linked list collection, there are 2 pointers. One is head, another one is tail. So we can get head, and we can also append one question to the linked list. We can also create iterator. Then we return, we pass the pointer to the linked list collection to the linked list iterator. Initially, for the linked list, head and tail are null pointers. Then we can append and free the linked list. So first we check append. So originally linked list is empty, so head is null pointer. Then in this case, if we want to append one question, then we new one item, right? New one item. Then for this just allocated item, we have a next pointer and this, right? This is data. This is next pointer, right? Like this. So originally head is null pointer, so we execute this line. So that means and tail and head both points here, right? Otherwise, if this is not case, then we will execute this line. This line means, for example, current status like this. So we can assume that current status like this. Then we will execute this line, tail points to that. That means send this pointer to this just allocated item, right? The new item. So this line means this. And then tail points to the new item. Okay. So head still points to the first item, and then tail points to the last item in the list. Okay. And this is how we append items into the list. Then if we want to clear the list, then we first check whether the head is null pointer or not. For this example, now tail is here, and the head is here. So apparently head is not null pointer, so we can go ahead, right? Go ahead. So first we get the head. We use P to points to head. This is P. Then we delete head, right? This should be a get next, right? Get next. Sorry about that. So I think this should be a get next, right? So P equals P is assigned to next pointer. So P will point to p equals this one, right? P equals this one. That means p will point to the next item. And then we delete where head points to. We will delete this part, and then head equals p means head again points here, right? So when element is deleted, then we check again whether head is null pointer or not. Then we go ahead. So in this case, we will iteratively delete the first item in the list until all the items in the list are deleted. Okay, then this is how we delete the linked list. I think when we learn data structure next semester, we will learn in more detail about this. Okay. Then for linked list iterator, if we check whether we have next, we just check whether current pointer is null pointer or not. Right? If it's not, then we are pointing to an item, right? So if we want to get next, we just get the current item, right? Current item. Then current item points to the next one, right? Points to the next one. So we want to enumerate the list. So this is actually, maybe this is current, for example. Then we first get the current one, then current points to next, right? Current points to next. So in this way, we can iteratively get the next element in the list. Okay. So this is how we implement the linked list iterator and linked list collection. Then we can use the iterator to enumerate all the elements using this, all the elements by has next and next. Okay, then we can answer all the questions in the collection. So this is iterator design pattern. So for collection, we want to enumerate each question. The enumeration should be independent of underlying data structure. So this is what we want. So either we use the linked list, or we use array, or we use DQ or stack, and anything we use. We want to, our enumeration should be independent of the underlying data structure. So iterator design pattern provides a way to access elements of an aggregate object. So it's a collection of objects sequentially without exposing its underlying representation. So the user does not need to know the underlying data structure, right? Maybe today I use an array, and tomorrow maybe I think linked list is better. I can change it to linked list. The user is not affected. Okay, then this is iterator design pattern. So actually, iterator design pattern is already implemented in STL. We know that so STL vector, STL list do all have this iterator design patterns. All have iterators. So actually, there are some implementation. So if you want to challenge, so you may try to read how these iterators are implemented in STL. I think this is really challenging for us to read. Anyway, if you have interest, I think you can find it. You can find it in a system directory, and you can find how it is written. Okay. Then using this template and iterator, we can have a better implementation. A simple version for this, we can just use it as if it is a pointer. So again, we implement this count if. So we have a predicate, and we also have input iterator. So this input iterator can be used as if it is a pointer. This is a pointer. Okay. So if we implement iterator, then the iterator supports this +1 and this dereferencing operator, then we can get this work, right? Actually, this is what we will introduce briefly later. So this is actually its concept. So if we want to implement some template, we want to ensure or require that the type, so this type input iterator supports this operation and this operation, then we can use concept to support template definition. Okay. So we will learn later. This is concept. This is concept. Actually, this is introduced in CPP20. Right? And then for conif, we can also implement the linked list. So if we use originally in previous example, we did not use template, right? Now we can use template to implement a more generalized linked list. Okay, so this is the linked list item, and this is data. So we can use the template. And then we have a next pointer, okay? Then this linked list iterator also has a template. So then the we have a linked list item here. So we provide the type here. Okay. Then we can support this dereferencing operator. So for this dereferencing operator, we are getting the data, right? Getting data. And then we can support this prefix unary operator +1. Right? So this +1 means, so the header of the linked list will go to the next one, then return current one. Right? We also have this operator overloaded, which checks so whether it's equal or not. Two iterators equal or not. Then this is how we implemented the linked list. Again, there's data type T here. And then we can push back for the linked list if you want to push back. We just use the linked list item to enable this pushback. So from this one, we can see that, for example, if originally we have this linked list, so this is the linked list, this is the head. And then if we want to push back another one, then we will new linked list, right? Oh. And actually, this pushback is push front, right? So, so the underlying implementation is push front. So we new an item here. So head will point to here. Head points here, and then previous head is the next. Right? Next will point to this previous head. Right? So actually, our underlying implementation for this pushback is a push front. Right? We are pushing front to the front one, right? To the front one in the linked list. If we regard this as head, right? This is the first one. Right? Then we are pushing front, right? Anyways, this is an implementation. I think it's easy to implement pushback if you want, right? You just add another pointer tail, right? Then you can push to implement the real pushback, right? And then begin will get the header returned, and end will get the null pointer, right? Okay, then we can use COUNTIF for the linked list. So we have this function used as predicate. Then we can use linked list to store all the float scores. You can push back scores. Then we can use COUNTIF, and then this is our own defined iterator. Then we can use iterator to count, right? Count, and use this predicate to count the number that passes the exam, right? So now COUNTIF is generic. It can be used for different type of data. Okay, and this is how we implement our own template linked list or template list. So actually, STL standard library, standard template library has its own implementation. We just mentioned that it's much more complicated. Okay, then this is generic program or generic algorithm. The COUNTIF has the following parts. One part is a general counting algorithm for a set of elements, and there's a predicate that may change in the future. So we can provide different predicate, then we get different results. So this is for counting rules, and then a collection with iterator to enumerate all the elements. So we do not need to know the data type and data structure underlying this collection. Right? So COUNTIF is a generic algorithm where the above three parts are decoupled. That is to say, the algorithm is independent of data types, data structure, and predicates. So it is a pure algorithm. So templates and the predicates enable generic programming. Okay, so from this example, we know that by using template and predicates, we can focus on generic algorithm programming, right? So STL is a good example for this generic programming. So now we will have some time to learn a little about this standard template library. Actually, this standard template library is now is complicated actually. So there's you can see that there are so this is a CPP reference. So from this CPP reference, we can see that there are many different stuffs here, right? So actually, I think for CPP reference, it targets for a reference, right? So targets for a reference, and that means it targets for all the maybe most of the grammars, especially for new grammars and different grammars in different versions of CPP criteria or version, right? So from this reference, we can see that first one is compiler support. So this is very important, I think. So for this compiler support, we can see that for different grammars, I just mentioned the concepts, right? So this for concepts, different compilers have different support here, right? So if we want to use concepts, for example, we have to use GCC 10. Right? We have to use GCC 10. Actually, for our class now, we did not have GCC 10, right? However, I think in this spring, it's April or May. GCC Spring is just released, right, in this spring. So if you have interest in testing concepts, you have to install the latest GCC by yourself. And I don't think there is a easy way to install this. So maybe you have to download all the tarball, all the source code and compile it by yourself, and then you can install it manually. We cannot use apt-get, I think. apt-get doesn't work currently for Ubuntu because this is a very new compiler. We cannot, actually is not yet prepared for Ubuntu's apt-get installation. Okay. So from this compiler support, you can see that for different grammars, different algorithms, we can use different versions of the compiler. So, or if we want to use some function, we have to have a higher version for this compiler, right? So from this compiler support, we know there are the constraints, right? If we want to use some functions, we have to use some versions of the compiler, either higher or equal to that required version. Okay, so this is the compiler support, and this is language. So actually, for this language, so it means there are some some basic grammars mentioned in this reference. However, I don't think this is a very good way to learn. So I still insist that if we want to learn something, we need to read some book or find some tutorial, because this is the target is used as a reference. That means we already learned it, and then we need a quick reference. Then we can refer to this. And if we want to know some latest grammars and in CPP 20, then we can see here, right? We can see all the latest grammars here. However, if we want to learn something, I don't think this is a very good way of learning, because the reference actually is not so readable. It serves as a reference. It is not a book. Okay. So there are some different different libraries and different this is concept library. I just mentioned that. So this is CPP 20. So in this concepts library, I just mentioned that it serves for template arguments. I'll mention about that later. And there are also some utility library and different functions and utility functions such as pair, optional. We already learned that, right? And there are some date time and smart pointers like that. So if we have some interest, we can check it in more detail. So this is string library. Actually, originally for this CPP reference, several years before, there's only a string library and containers, right? And algorithm library. I think several years before, there are only such libraries, and also input-output library. Then all these other stuff are incrementally added. And as we know, some libraries already implemented in templates. So this originally the STL refers to container, iterator, and algorithm. Now concepts, also some generic utility libraries also use templates, right? So the boundary of standard template library is not so clear now. Many different parts have templates. Okay, so there are also some thread support. You can see here, and atomic operation library. So these are for concurrent programming. And there's also regular expression library. This is introduced as this CPP 11. We know that regular expressions works best for Perl and Python, right? Now in CPP language, it also works. Okay, anyways, so this is a standard template library. If we want to learn something, we can use this quick reference. So especially for this container library. Because I just mentioned that the other parts are added later. So for the other parts, there are few examples actually. However, for this container library, because it has some, I think this lasts for years. So there are many different examples, I think. And so for example here, so there are some example. This is for a priority queue. So you can run the example here. So we can see that even in this CPP reference, there's no CPP20. So no CPP20. We cannot use CPP20. That means even there are some examples for CPP20 grammar, we cannot compile it here, right? Compile it online, we cannot. So anyways, for these examples, because it's not CPP20, so we can run it. So these are outputs. So I think container library is very good because there are many examples. You can run the example and you know how to use it by examples. For other parts, it may not be so readable. So I suggest you to find some book if you want to learn some grammar. Okay, so this is just mentioned that original STL, there are 3 basic parts. So algorithm, predicates, and also a container iterator. And now there are more CPP templates. I just mentioned that concepts library is for compile time validation of template arguments. So we can require that the template argument support some operation, right? And can also do function dispatch based on the property of the types. And there are some smart pointers in the templates. Weak pointer, shared pointer, like that. Also regular expressions library. This atomic operation library is for locally concurrent programming. That means if we declare some atomic operation, then this operation will, we do not need a lock. Maybe some students do not know concurrent programming yet. So for example, concurrent programming means we have multi-thread, thread 1 and thread 2. So if we want to, for example, I++, if 2 threads execute this, then I will plus 2. Right? I will plus 2. So if we do not want this exam, this results, then we have to lock it. Right? Each time we access I by 1, right? Access I by one thread, right? There are 2 threads. So anyways, in this summer, we will learn multi-thread programming. Then we will know better about this. So this atomic operation, using this atomic operation, we do not need a lock. Otherwise, we need a lock here. It's a mutex. Mutex is a very typical lock. So this is atomic operation, and there are some most functions and structures in utility library, and they have templates. Right? We have learned this optional before. And we also actually there are also some. This variant is a type safe union. Actually, it's a replace of union. Okay. So using STL, we can easily implement this passing rate. So we define this passing rate like this. So we have the iterator and predicate again, and we use COUNTIF. So this COUNTIF is from STL. In STL, there is a COUNTIF function for us to use. I think it is in the utility library. Then we can use a vector to store all the given scores, and then we can use bind. So this is also from STL, so we can use bind, and this is also from STL. We will learn. Actually, we may not have time to learn more detail. So this greater and equal is a template. So we provide a type for this. So it is used to compare between 2 float variables. And then this bind will bind it because it takes two arguments. Then if we want to always compare with 60, then we can bind the second parameter, right? So this one, this is the placeholder, so this is for obtaining the first argument for passed into this greater equal. Right? So this first argument is placed here, and then this the second argument. So that means greater equal will always take one element from the vector, then place it here, and then compare with 60. So this is bind. Right? So that means we will always compare with 60, right? Whether it is greater or equal to 60. Right? So similarly, this is also bind. We can also use it. You can use it for an array. Right? So this is how we use the template for passing rate in using this STL. Right? Okay, then there's some STL containers, the sequence containers and associative containers, and also some other containers like DQ, priority queue, stack. There's also STL span, std span. This is latest grammar, so we can use it to access a continuous sequence of objects. So we need the latest compiler if we want to test it. Then this is concepts. So I just mentioned that. Okay, let's have a 5-minute break. We will come back later. Okay, let's continue our class. We need to quickly finish our class, then we will have some in-class talk. So a class template, function template, and non-template functions, they're typically members of class templates and may be associated with a constraint. So this concept relates to a constraint. So this constraint specifies the requirements on the template arguments, which can be used to select most appropriate function overloads and template specializations. So this is for, I just, for this previous example, we are always worrying about our template being misused, right? So if some people, some user pass a wrong type into our template, then it will get error, right? So if we want to, during compilation, we can do some requirements, give some requirements here, then it avoids such problem. So this is the basic concept for this concept, right? So concepts is named sets of such requirements. So it is actually a predicate. So evaluated at runtime, evaluated at compile time, and a part of the interface of template where it is used as a constraint. So it is, when we define the template, it will be provided in the template, okay? So this is the basic concept for this concept when we define template. So these are the core concept for template. For example, maybe we want this two type to have same value. And also, if maybe for this template, we want to pass one base class and one derived class, right? So this concept is derived from. So this is core language concept. Sometimes we want to have such kind of constraints for our template to be correctly used, right? So this is one example. Is for provided concept regular. So this regular concept means it specifies that a type is regular. A type is regular means it can be copied and has a default constructible, right? And we can compare different values of this type. So this is how we define the template using this regular. We can use this regular here. So we specify this, the type should be regular, right? So this is requirement or constraint. So this is the template, how we use it. Actually, the usage is similar with our previous templates. Okay, then for iterator, so actually iterator, we have learned that before. We have an iterator design pattern, and then in the STL, there's also iterator. Actually, starting from CPP 17, we have the different categories of iterators. Some is for input and output, and then forward, and bidirectional, and then random access, and then continuous iterator. So there are different types. Actually, I think for now, we can just use our original usage, because CPP 20 are introducing a new system of iterators based on concepts. So there are a set of interfaces for this new iterator. So I suggest you, if you have interest, you can learn it and then use a new system of iterators in the future, okay? And also there are some built-in function objects. So we have used this greater equal, right? We just use this. So there are some arithmetic operations and comparisons. And there are also some logical operations, bitwise operations, and also some range equal to. So this is constraint comparison. So we just mentioned constraint, right? Constraint, this is concept actually. So there are some, some constraints on the arguments. So for this type, this kind of comparison, there are some constraints for the arguments. Okay. And there are some support for function objects. So we can use this function. So we can wrap some callable object that is function object, or just a function, right? So we can wrap it into another function or a parameter, right? or variable. So actually, there are some for this one. There are some example in the reference, CPP reference. I suggest you to try it. I think for many different functions, there are some examples. You can try it. Okay. So, anyways, there are different wrappers and support functions for function objects. So, if you have the interest, you can try it. Okay. So, there's also STL algorithm. So, algorithm defines functions for a variety of purposes, for searching, for sorting, for counting, etc. So, there are many different algorithms actually, and function objects are used in these algorithms. So these are the algorithms. There's for this set of algorithms. So this is actually from CPP reference. So I think for most of them, there should be some examples. So I think for learning these algorithms, examples are very important. So I suggest you to check the examples in this page, in the CPP ref. Then you can know better. You can run the example. So this is modifying sequence operation. That means it will modify the sequence if we use the algorithm. Okay. And this is also modifying sequence operations. Partition is used to partition different sets of elements, partition the range of elements into two groups, for example. And there are sorting operations. We have sort and stable sort. So stable sort, I think we have an example. And there are some binary search operations, and also some other operations on sorted ranges. So this is for merge sort, I think. It's for merge two sorted ranges. So, and there are also some heap operations. So we can make a heap, and then we can use heap to sort. And there are also some max minimum operations, also some comparison operations, perturbation operations, and numeric operations. And also some operations for uninitialized memory. So that means we do not require that the memory is initialized. So for the stable sort, for example, there are many different examples in the CPP reference website. So I suggest you to check it and run it if you have some interest. And then for the stable sort, it stores elements in the range like a sort. However, stable sort keeps relative order of the elements. That means if the two elements have the same value in the comparison, then it will keep the original order without changing order. So for checking this stable sort, so verifying this stable sort, we have this compare as int function. That means we compare two float values by their integer values. Okay, so if we have this array of float values, then we can use stable sort on it. When we use stable sort, it will sort all the algorithm, all the elements according to their values, right? So in this case, it will sort all the elements. However, if we do stable sort on this function, we compare the values by integer and by their integer values, then it will keep the relative order. For example, for this one, so for this one is compared because this one actually the value is smaller than this one, so it will switch, right? However, their integer values are equal, so it will keep the relative order. So relative order is this. This 2.72 is prior to this 2.58. So it will keep the relative order. So anyway, this is one very simple example. So if you have interest, you can check it. You check more algorithms in more detail. Okay. So this is summary and